When we start thinking about lambda calculus, we can often find a list of rules which can be confusing and in fact challenge us to wonder why we need to know these. So let's back up to a simpler question. What do we know about substitution already? What can we borrow? And what might tempt us to think we need better understanding? The simple question that we'll be asking here is whether a constant function should ever be treated as an identity function, and what the rules of substitution ought to say about that question. So we begin with what the concept of a variable is. Normally, we would say a variable can be treated as a place we're going to fill in blanks. If we write f of x equals x plus 5, that could easily become, in our minds, f of an open box equaling the open box plus 5. Within that box, we can fill in whatever symbols we like. Here, the number 3, and it starts to take on a meaning. That box really is in our minds most of the time. We've gotten accustomed to simply replacing the x directly with the symbols we have, and this has become the substitution we've understood throughout most of our understanding of algebra. And from this understanding, two very simplistic but enormously powerful functions immediately emerge. First on this list would be the constant functions. For example, f of x equals 5 always gives us 5. The horizontal line at the level 5 indicates that in a figure. G of y equals pi is a more complex version of the same idea. Here, we're not articulating what constant we actually mean. It's hidden by the symbol pi. We understand it to mean 3.14 with an ever-adjusted precision. And the use of y is just to show off that we are not scared about renaming our variables as necessary. H of u could also equal something like cat. If we're going to allow pi as a representative of a number, we may as well allow any symbols as representatives of whatever concepts we want functions to deal with. A word, the concept of an actual physical cat, or anything in between. And from these, we realize we could capture even these concepts with a new function, a function now depending on two variables. The first would be a c, and the second would be the variable we want to substitute when we think of the constant function. So, capital K sub c of x always outputs the specific constant c, whether c be 5, pi, or cat, and thus we've named all constant functions in one uniform way. It's a simple concept, but becomes powerful in implementation. The second of our main functions are the identity functions. And here we certainly see three symbolically different functions. F of x equals x, g of y equals y, h of u equals u. But upon substituting, we realize in our minds each one of those variables will be replaced with an open box upon which we substitute identically the input for the output. This nature of equivalent substitution leads us to think it's natural to not concern ourselves with the names of variables, but simply the manner in which they affect substitution. We don't worry about whether f, g, and h are differently named. We care about whether they input and output differently. It's a form of extensionality. These are distinct symbols, but identical functions. We now call this the single identity function. Every input is reflected identically as the output. So what must these two simple functions do? They must coexist. But in doing so, we provoke a problem. The constant function, as we saw before, simply takes in the constant we want and the value x. Forgive me, right here I had mistaken the value x for c. It's now been corrected. With this constant function, we know what the outputs will be. They will never change, they will always be c. And the identity is the different. Every input is reflected identically as the output, and therefore every input changes the output. These are drastically different conceptual ideas of functions. So then what in the laws of substitution explains what we should do with this function, k sub x of x? We know from the first rule that the c is replaced with x, and therefore we know that the outcome is the constant x. And yet, upon performing a change of the input x in parentheses, it'll affect the outcome. What are we to say about this? Is this a constant and never changing function, or is it more like the identity, always reflecting the changes of the input? And what law of substitution guides us to make the correct and consistent answer to this question? The answers are none. In truth, we've left substitution as an informal concept with imprecise rules that cannot be tamed. And to make them precise requires that we impose rules. But imposing rules begins to make a theory. A theory will have limitations, won't prove everything. There will be some things that are left out, and that may concern us as we've been using substitution in a freewheeling way for so long. Will we perhaps ban some substitutions that are enormously powerful, like recursion? The repeating of a variable inside of a function lets us compactly trace out how we repeat our steps. But we've seen that a willy-nilly use of variables might not be something that's consistently applicable, and if we're too quick to erase the rules, we may lose powerful functions. Also, imposing rules increases the chances of new paradoxes between the rules themselves. How do we make sure that we produce something that is consistent and will not lead to new problems? And if the rules are consistent, they might also be rather complex in order to avoid paradoxes that emerge in the middle. These we need to look out for. And it starts to make us question whether we know that this is an algorithm. Does substitution always come to an end? Will the rules be strong enough to alert us to that consequence? All this has been worked out over about a century of work, beginning with Alonzo Church, who offered up a form of what's now known as lambda-calculus. It was soon seen that it was actually equivalent to another computational model by Turing, his notion of computation. Today we have these summarized in two very popular phrases, both within mathematics and computer science. Turing machines are today's universal computers. They can perform anything that any present, future, or past computer can do, and perhaps much more. Lambda-calculus, on the other hand, is a universal programming language. Any set of algorithms you wish to program can be written and expressed completely in the lambda-calculus, and therefore they will outlast any present trends and jargon. Getting to be familiar with both the rules of Turing machines and programming languages, and the fact that they're interchangeable, is the start of most programming challenges and mathematical reasoning. They're worthwhile investing in, and the simple reason to get started is as simple as asking whether you understand how to substitute and always come up with a consistent answer.